Hello, good afternoon, everybody. Please let me know whether you can hear me well or not. Okay, good. Welcome to our lecture. Today lecture is on the simulation of wire drawing process. Last week we talked about we introduced the wire drawing process, and then we talked about some theoretical background and some theoretical, I can say some analytical calculation for drawing force and for plastic strain and so on. I introduced a little bit some simulation which have been carried out with abacus, and we reviewed the result. But today the plan is I will simulate a wire drawing process using the Zimofact software, and at the same time I will share my monitor for you, then so we can go together and step by step and to understand how you can set up a simulation in metal forming simulator generally. Okay, the reason I have selected Zimofact is that I said before that abacus interface and abacus is totally different, but the other software like Deform, Zimofact, and Qform and the other software, more or less the interface are similar. So if you understand and if you become familiar with one of them, then you can handle your simulation in any metal forming simulator with more or less. So this is the first reason, and the second reason is that Zimofact is a German software, so I have choose Zimofact for our simulation, but it doesn't matter. Just the purpose is becoming familiar with the simulation steps from the beginning to the end. Even maybe I make a mistake, then we will get a error, maybe yes or not. Okay, let's see. We will get some error, and then we can solve it together. So I think that this kind of training for the software would be beneficial and useful for you for your future. And then later I will compare some result of the simulation with some theoretical concept we reviewed last week. Okay, so of course you have some material, which the PPT, and the PPT I tried to write down the steps on PPT, but I will not follow the PPT. Maybe the sequence will be different, but what you have done, whatever you have done for a simulation, of course it's in PPT, but here maybe the sequence will be a little different because I will do the simulation online with you. Okay, so this is the environment. This is the interface of Zimofact software, as you can see. And to start, there is a button here for new project. So I start the simulation by clicking on this button, and then you have these options here. Okay, as you can see, you can simulate different kind of simulation process, and even heat treatment and welding using and mechanical joining even using Zimofact. However, these are the available metal forming process which wire drawing is not included here. So I will select the general option, So in the general option, you can set up your simulation, your deformation simulation, in the way you want. Of course, you can set up a rolling even here, or cold forming or ring rolling here. But if your process is designed here, then you can choose the related bottom, and then the setting will be much more easier for you. However, you can simulate any the deformation process using this option general. Okay, let's go on. Now we have to choose the process type and some other parameters to prepare the field to start the simulation. Okay. So again, I choose general here because our process wire drawing is not categorized here. Then of course it's a 2D axisymmetric, because wire drawing you can the best option for wire drawing simulation is a 2D axisymmetric, because your sample has an excess of axisymmetry. Then you can obtain the result much more faster if you use this option. Of course, you can do it with 3D and not with 2D but with 3D. Then the result of your simulation more or less will be same with 2D. However, the time of simulation will increase if you simulate this process with 3D option. And then the solver type, of course, we use the finite element, because finite volume, as we explained before, it's not adapted for this kind of metal forming process. It's much more for CFD simulation. And the room temperature 20, the number of die, of course we have a die and we have a puller, which pull the material or draw the material. So we have 2 dies. So we select 2 here and then apply, and we can go to the next step. Okay, this is the interface for simulating our process. Now the first step is bringing the geometry to our simulation. It's better I check the slide at the same time. So okay, if you check your PPT, the PPT we have a problem description. In the problem description, the parameters for the process we want to simulate are given. For example, it's a single stage wire drawing. It's isothermal, of course isothermal because it's at room temperature then, and the material is copper. Last week we started and we simulated the simulation on copper, so I used the same material data, and we will bring it from that paper, the data again, to the software ZeroFact. And option is frictionless. However, we can give some value for friction even, and then the die speed and whatever we want. And the geometry also are given here in the slide number 5. So basically we have 3 parts: the workpiece, the die, and the puller or drawer. But okay, for drawer it's not important. We can put whatever there, and just we can attach the material to the puller. But the other geometries are here. So for loading the geometry, I choose right click here and then geometry, and from file. And from file, first I bring the die, and you can prepare it in these formats. Okay, I prefer STL for. Okay, so if I click, then you can see that this is the die, and exactly the die one of the die we had the result of the simulation for that using Abacus last week. This is the same. Okay, and the the next, again, I load the upload this is the die and the workpiece here. Okay, the workpiece. And for the puller, let's see, do I have something here? Yeah, for the puller also, of course, I have already designed the part, so this is the puller. Okay, now we have to set. First, we should allocate the available geometries to the associated parts here. Okay, the information of die and the initial, for example, the initial diameter, the final diameter, the semi-angle of die, alpha, and other parameters for this die are given in slide number 6. So you can check it if you want. And even the relief angle is given 54 degrees. So, okay, to allocate the geometries, just I drag the die to die number 1 in this way, and the drawer for die number 2, and the workpiece, I drag it into the workpiece in this way. So now the geometries are located, but the setup is not correct. Okay, I could design everything in the right way in SolidWorks in that way. When you load the geometries, everything will be set up perfectly. But by purpose, I did not do, because I want to teach you how you can set up your drawing process. So let's start. This would be okay. First, I click on the workpiece, and then right click, and you have option for positioning here. And when you open the positioning, this would be the most easiest option available. So in this way, I can move the workpiece regarding to the die. So let's do it center, X center, Y center, and die also. So the center of the workpiece will be matched with the center of die. And when I click OK, it becomes in the center. Okay, but we do not know in Z direction, in Y direction, here in Y direction, is it located in the correct way? Is it located at the correct place or not? Okay, let's see. To check, you can apply a cut here in this way using this option. If you click, it's not coming here. Okay, let's again. Okay, maybe if I okay, it's here. Okay, then I close the video in that way, then it would be much more better. Okay, so if you click this clipping option, then we can make a cut on YZ direction here. YZ. Okay, now if I rotate it in this way, okay, you can see how it's located. So we have to move it a little bit forward, the workpiece. So I click here again the positioning, and in this time in Y direction, you can move in Y direction, and the interval like 10 for example, then back here. Okay, and it should be located nearby the die, so we can come forward a little bit, then it's okay. And this puller should be in contact with the material. So again, positioning, and I use this option. I want to move the drawer in Y direction, so the maximum of the drawer should be located on the minimum of the workpiece in Y. Let's see, does it work? Oh, it seems that it is located at the right place. Okay, done. So now I have prepared the setup in this way. So if you have question at any stage, then you can write down your question. I try to check both monitors and catch your question. Okay, let's go to the next step. Okay, the next step is the material properties. Then now we have to allocate some material properties to the simulation. Material. Okay, you have three options. I will use the manual option and the library both, then you can experience both of them. For the material, what you have is, what is important is mechanical properties and the flow curves, because it's a cold simulation, so you don't need to care about the thermal properties that much. For the mechanical properties, Young modulus is important. You can give it in table form. It means that it can be a function of, for example, temperature or whatever, but here we give a constant value for that, and that constant value is 1.33 e to the power of 11. Okay, the Poisson ratio, of course, you can give in the tabular mode, or you can give a constant value simply like this, and a constant value for the density, which is 8960 kilogram per meter square. Okay, you can see this software, you have the unit here and you can change the unit, but as I said, if you remember, I said last week, the Abacus software, it's a unitless software, so you cannot see a unit in Abacus. Then you should be careful about the units. The units should be coherent in your simulation. If it's not, then your result will not be accurate. And and for the flow curve, we have one temperature, because the room temperature, and one strain rate. If you remember, we had the curve, and you can check the slide number 11. It was 0.0016 for the strain rate. Then if you have many temperatures, then you should give the other temperatures and the other strain rate, and for each couple you should give the data for that. But here we have just to import a set of data here. Then when you click on this button, you have the table here. You can fill out the table giving the effective plastic strain and flow stress. Of course, it's plastic flow stress. But okay, I have prepared the Excel file before, so I just upload it to save the time. Oops. Okay, let's see. If it doesn't work, then oh, this is not the right format, so maybe this is not the file. Let's check. Can we find another file here? No. Okay, then I can open the file and I can input the data. So, okay, let's give the data. It takes time a little bit, but it should work. It's semicolon, everything is set. Let's try it once more. Maybe we can semicolon. The X value appears multi-time in the list. Reading stops. What? Maybe if we delete these two rows here, then we can try once more. Okay, then we can see sometimes you encounter some problems during the simulation. Then, oh no, okay. I will give it manually. It doesn't matter. So, for this value 0.0258, then Pascal, we can make it in megapascal, then 210. Okay, and then 0.0525. Then you can add what, if you want, if you need more rows, then you can add, and then okay. And I think that would be enough up to here, maybe. Okay. We need a zero value here for the first one, and I think we cannot add a row there, so okay, if we make it 0 and then like this, it's not correct, but okay, it solves the problem in this way. So back to the simulation. Okay, now the flow curves is given. Okay, it's not complete, but I think it's okay. The mechanical properties, the flow curve, and we should upload another material for the die. For this one, I use the library of the software. Here, some tool material, and some for other alloy, some material database is available. Because we need the tool material, then I select the tool material and I choose the rigid tool material, which does not deform during the deformation, and then I upload it here. Then I should allocate this one to the drawer and this one to the die, and this material for the workpiece. So of course we can rename it in copper, whatever. So the workpiece now, it has the mechanical properties of copper, and the die, both dies are assumed to be rigid. Now we can go forward, and the next step is giving the press speed. Here I choose the manual. Here you can see that some mechanical press, if you want to give, for example, for forging, then you can give the parameters for the press, but in this case we want to use the tabular mode, and so then we should give at least 2 rows at the time 0 beginning. This is the direction in y direction, and minus, because this is the drawer should move in this direction. This is the minus y, so I give a value of minus 10 here, and then for next one, after, for example, 35 seconds, again constant speed in y direction, and apply. Okay, and then I allocate this one to the process, and you should take one more step here, because now you have designed the press, the motion, and it's allocated to the process, but it's not connected to none of the die. So if you right click on this, then you have this option, add die to the press. Which die should be connected to this press? The drawer, because the drawer should move. Okay, and then okay, now it's done. The next step, we should define the friction value. Okay, again you have 2 options, manual. I use the manual option even, but if you go in the library, then you can see that the some pre-designed condition for the friction, for example, say this lubricant, that lubricant, are listed there, and based on the lubricant and material you're using, you can use the data from library. But here I use a manual, the chrome friction, and for example 0.05, or even we can give 0, because it's we are trying to simulate a frictionless process. And then it should be allocated to both dies, the die and the drawer. And although the process is isothermal at room temperature, but you should give the thermal option, because without this simulation will not run. So I open the thermal option, and for this, and this one should be also a constant value, but this information will not be used, just we are making the option and for the workpiece. Okay, I will not change. However, if you want to change some values here, you can change the heat transfer coefficient to the workpiece, the emissivity for heat radiation to environment, and what's the any parameter which is about the thermal properties, you can define it here. And then we should allocate it to dies, and this one to the workpiece. And more or less we are done. Okay, now okay, remember that our simulation is a 2D simulation and it's axisymmetric, so you should check how the axisymmetric plane, or how the axisymmetric axis is located. So if you click on this 2D simulation, okay, then you can see, and then you can check that is it located in the right way or not. It is not. Okay, so so I think we should turn our setup, and we should rotate it, not by here, but let's try this option. So this is the which is this. It's located at x direction, so everything should be aligned with the x direction. So in that way, then again we come to the positioning, and this time rotation, it should be on the x direction. Then just 90 degree and then rotate. What happened? Let's see. Where is the x direction? It's there, so okay, we should choose Z here, and then now it's okay, it's correct. And then this one again, okay, positioning, rotate, Z direction 90 degree, and then apply this one. And for the die also, positioning again in Z direction and 90 degree and apply. Okay, let's see. This is the reason we cannot see everything. Okay. Okay, we should find the drawer, so I hide this one, and again we should reposition the drawer in this way, the drawer with the material, the workpiece. Y and Z should be centered, both, and the Z, the X, the maximum to the minimum. Once more. Drawer to the workpiece. In X direction, the maximum to the minimum. Why it doesn't move? Okay. And then die and okay, once more cut. We need a cut in XY direction this time, and then we should check it. Oops, it's not correct when we see here. Then we should rotate the die again. Okay. Let's apply the cut and then rotate it. We should rotate the die around the Z direction for 180 maybe, and then okay. And again, position the die with respect to the workpiece for Z and Y, center, okay. Now let's see this option. Okay, now the plane of axis symmetry is located again in the right direction. Okay. Still it's wrong. This is the Z direction. So we set everything in, not in Z direction, but in X direction, I think. Okay, I don't know, we cannot rotate it, rotate the axis here. So back to the positioning option again. Oh my god. Then now in the Y direction, I think we should rotate 90 degrees. What happened? It's not rotated. 90 degree in around Y direction. Okay, and this one degree again. And oh no, this is the die. Okay, let's hide it so we can find the okay, let's check this one. Is it? No. Okay, now it's okay. Just we should set the drawer at the correct position. Just we should. Okay. Let's hide it and then rotate it. Okay. And then again, the Y, X and Y should be centered. This way, okay. And then the Z, the maximum should be located on the minimum. Oh no, vice versa, the minimum and the maximum. Okay. And then, okay. And if we go, no, okay. Now it's correct. So this is the plane of axis symmetry and this is the setup. Okay, this is down, and then okay, one important thing is the contact, because you should define what's the contact between the drawer and the material. Of course, should be glued or should be joined together, because it should be able to draw the material, and even between the material and die. So the option here is you should insert a contact table here. When you open the contact table, then workpiece with the drawer Okay, this should be glued, and then workpiece with the die touching, it's okay, and okay, then I think everything is okay. Apply. Okay, and this is about the contact between the material with the workpiece, the die, and the drawer. And one more thing you have to set up is the forming option here. So you should give how much is your stroke, or the time, the total time, for example 35 seconds here, or whatever, or 25, or we can give 30. And then in the sub stage, of course, you have to choose at least one of these options. These are the other options for example, for forging, dwell time before forging, dwell time after forging, and are the other options which are available. And this is for the output divisions. The number of the steps will be recorded in the post processor, and you can see. Then I increase it to 100. So this is down, and okay. Now we can check the simulation whether it's work or not. I don't know, maybe still there would be some problem. Okay, we need to save it. We save it as project number, name it class in the folder. Okay, we forgot to make a mesh here for the workpiece. So if I click here, then the options for the meshing is available here. This is the recommended mesh system from the software based on your geometry and based on your process and what else. So we can change this only the size of the mesh and then create the mesh. Okay, yes, and again I try to run the simulation. Okay, now it's running. If you want to check the result, then you can view the result in this way, and why it's not showing any deformation? Okay. You know, I think we have a mistake here in the table, because we turned the setup. So now the movement should be in the Z direction, not in the Y direction. Okay. So I erase the data, because if you do not erase it, you cannot edit it. Then I go back to the table and then -10 here in Z direction, -10. Is it minus or plus? Not minus, but +10. This is 0, 0, 10, and 10. Okay. Let's check it. Where is it? Run it again. Okay, now it's working well. So now you can see the effective strain distribution, the graph, and you can check whatever you want. For example, effective stress if you want to see, and the temperature. Of course, temperature is giving nothing here, and the other options for the different values of stress, strain, displacement, and whatever you want you can choose, and you can check your result. Okay, good. So finally we could finish it. You know, I encountered many problems, even if I have prepared it before, but okay, you can see, but it's good because it was kind of challenge for me and you. Then we could see how should solve the problem and obtain the result. This is if you start the simulation, or if you start working in the simulation field, then you should know that you cannot obtain the result with a single try. Of course, you should try and try and modify your simulation, and finally you can obtain some meaningful results. Okay, back to the plastic effective strain. Okay, so the result is more or less similar to what we had last week in our simulation. You can see the distribution of a plastic effective strain on the surface is almost on the surface is maximum, and then toward the center its value decreases. So I'm waiting to see. Okay, from now on we can shift to the PPT. So we finished this section, the first section. Okay, now in the way I explained, I have prepared and I have run some simulation, some other simulation, by changing the coefficient of friction, the Coulomb friction. So you know our simulation is running now with mu equal to 0, then I'll save the result, then I rerun it with mu equal to 0.05 and then mu 0.1, and then in the output, okay, if I go back to the result here, there is option here. If you click it, then you can have this is the force displacement or force time curve. It's a little bit different with what you have there, because you know the average option is not applied. If you apply the average, then you can see here the material is not in contact with the die, then it becomes, it's touching the die, and then full contact and deformation, and here the material is going out from the die, so the force is decreasing. So similar to this curve, now I prepared, you know, this is for this 0.05 mu, and then here I'm comparing the result for 3 different conditions, for frictionless 0.1 and 0.05. I obtained the drawing force using the simulations. Okay, of course the maximum is important here, and also I calculated this force required for wire drawing using the equations we have developed, we have derived last week, if you remember. So I asked to make this file in Excel as a homework, so I did it also, and I gave the dimensions and the alpha for the die and the mu value, and then I obtained this value for drawing force here. And if you compare, for example, in the case of 0.05, the maximum is almost maybe 900, but here the calculated value is 625 kilonewton, and in the case of mu equal to 0.1, it's here it's 781, and but here it's 1100 something. So we talked about it last week. What's the source of this error? The source of error, if you remember, it's exactly from our last week lecture. We have 4 main assumption in this method, which is based on the force equilibrium analysis. That the first and the most important assumption is that it's in absence of the redundant work. We do not consider the redundant work. So that in this, using this equation, the deformation is performed under using a lower force, because we are not considering the redundant work. If we consider it, then it will jump up. So this result is showing that maybe 25-30% it's lower than the actual value. We can say that what simulation is predicting is the actual value here. And of course, another assumption that its friction is constant, but friction is not constant. Even we have given the friction constant in our simulation, but if you go back to the simulation, there is an option. Basically the friction at least should be a function of pressure, because at the higher pressure more friction you have, and the lower pressure the friction reduces. So if you give the friction pressure dependent, then you will obtain some better result even in simulation. But and the other case is that the metal does not work harden. In this case you give a constant value of y, the yield stress, and we are not considering the work hardening effect. However, in software we gave the curve and we obtained the simulation result. Okay, so let's try. This is another try. I want to exclude the effect of work hardening. Okay, we can assume in the simulation we can assume that the material is not work hardened, and so we can give a constant value for the flow stress here, and this is the value 300 megapascal. So I gave the same value, a constant value here in the table, and then I run the simulation again, and okay, this is the result. This is the maximum. It's about 850, and the force is still 500 kilonewton. So still, even we remove this error between the simulation and the analytical approach, still there is a big difference, which is mainly is related to this option, because we are not considering the redundant work in this calculation, but in the simulation it's fully considered. Okay, and the last topic is investigating the influence of die semiangle on the drawing force. If you remember, last week we had such a curve, and we talked about it, that why this is the drawing force and this is the die semiangle. At the beginning, by if you assume that the reduction of area is constant, so it means that the initial diameter and the final diameter are constant, just we are changing this angle here. So at the beginning, by increasing the alpha, the drawing force reduces. I told the reason last week, because the surface between the material, the contact surface between the material and the die is much more bigger at the smaller die semiangle. So by increasing the die semiangle, this area becomes smaller, so the friction reduces. So this is the reason. And after that, then it starts to increase again, and then here you have a dead metal zone, so it doesn't matter. By changing the angle, the forming area will not change, and then at the final stage it decreases because of the shaving phenomena. So let's investigate this curve, especially in this area of the curve, using a simulation. So this is a wire drawing simulation. The sizes are more realistic compared to the previous simulation. We just use it for a teaching or a tutorial material, but here the initial diameter is 4 millimeter and the final diameter is 3 millimeter. The die angle is 13 and not fixed 13, I think it's 7 8 13 14, and okay, I had to correct this slide, and the constant value of friction. So at least I had to run for 5 cases of simulation. I did it before, but exactly same with the process we reviewed together for the simulation step by step. So these are the results. This is for the die with the angle of 14 here, and this is the drawing force, the maximum drawing force, 0.82 kilonewton. And then nothing is changed, everything is changing, everything is fixed, just the die angle is changing. So when it's 13, then it's a little bit higher compared to 0.82, and then for the 8 it increases again for with to the value of 1.12 kilonewton, and then this is the last case with the alpha equal to 17, and then this is the drawing force again decreases. So if I simply plotted the value we obtained for the peak maximum drawing force and with respect to the alpha, the degree, and then you can see this is exactly what is shown here, but just in a small area, like here to here. So if we give the much more smaller alpha for the simulation, I didn't have enough time to make it complete, but if you can try it using the abacus, because you have the student version for abacus, then you can set up your drawing simulation, and then you can redraw, or you can regenerate or obtain this curve exactly, maybe by running 20 simulations. You can obtain almost the all of this plot. So okay, and I think this was the last slide on the topic of simulation of wire drawing process. Okay, today's lecture was a little bit short, and if you have any question on this topic, on the simulation, then I'm ready to hear and answer your question. Okay, there is no question. So this was our last lecture in 2021. Next week I think we will not have a lecture because the university asked to not giving a lecture on the last week. So our next lecture will be in the first week of January 2022, I think. Okay, so I close this session, and hope that you enjoy your vacation, and see you next year.